So the next thing we are going to look at now to complete the equipment check is beam spread. This is just mostly for knowledge sake because how the beam spread on your probe at the end of the day will ultimately be determined by the results you are going to get. But you should be able to physically be able to do what we call plotting of the beam spread. You should be able to plot it. Theoretically, we know that, say this is my probe, represented schematically like this. This is my probe. When the UT beam comes, it doesn't go straight, it spreads out. Just like your torchlights. You switch on your torchlight, the beam spreads out. So this angle that the UT beam spreads with is what we call the beam spread. Mathematically, we normally calculate it. Depends on, I am writing the formula this way so that some people don't get confused, because sometimes some people mistakenly calculate this full one and call it as beam spread, or calculate this one and they just mix it up. If you are calculating this complete, it means you have to do divide by 2. If you are calculating just one, if you are using sin theta, just know that it is half angle you are calculating. So which means at the end of the day, when you are done calculating, you multiply by 2. To save yourself that stress, you can just come here and say sine of half angle, which is alpha. By the time you do your calculation and get the value for alpha, that gives you your beam spread. So for every probe, for every 0-degree probe, you can calculate the beam spread very easily. Just look at the probe. In the body of every probe, if you look at this, it is clearly written as a 10 mm diameter, 4 megahertz. So instead of using this first formula, because we cannot easily get the wavelength, we know that wavelength is to calculate wavelength is velocity over frequency. If you put it into this formula, you are going to get this. So if you put the value of the frequency, put the value of the diameter, and the velocity of the material, because you are using 0-degree. If you are calculating beam spread for angle probe, please note the difference in the velocity that you're using. But since we are talking about 0-degree, we can use our normal 5920. So if I want to calculate the beam spread for this probe, it's just a matter of sine of the half angle in this case now will be K. K is a constant because we are looking at the full beam spread at 100%. We can use 1.22 multiplied by the velocity 5920 multiplied by the diameter, which is a 10 divided by 1000. If you want to convert it to meter, multiply by frequency 4 times 10 to the power of 6. That will give you the sign of the alpha. And by the time you do the inverse at the end of the day, mathematically you should be able to get the beam spread. This is theoretically. But we can say, instead of going through this route, and let's say we get our beam spread, let's say, for example, to say 15.2 as our beam spread, or whatever the value may be, if we continue this. Which means we are going to have a probe that will be spreading out at an angle of 15.2. Though a small angle, it may not be, this is not drawn to scale. We will now have 15.2 as the spread. But we can verify that by doing what we call the beam spread plotting. And we'll see it how a particular probe spreads with respect to the machine or the equipment that you are using. So theoretically you know it, but practically how do you check if the beam spread that you calculated theoretically is actually matching what is happening in real life when you do the connection? So what do we do? How do we do our beam spread? How do we plot it? So take note, if I have a probe on a material, let's say the material is this thick. The longer the beam goes, as it goes deeper into the material, the more it continues to spread. So which means physical distance versus the spread. The spread will be seen as changes in the diameter of the beam. Changes in the diameter of the beam. Take note, if we have this as the center of the beam. So if we can figure out a way to get this distance and plot it, this diameter, say D1, D2, D3, D4. Take note, I can call this as my distance 1, distance 2, distance 3, distance 4. If I can figure out a way to get the value of D1 to D4, capital D1 and small letter D1 to D4, and I plot it in a graph, that will give me my, okay, this is for angle group, and I plot it in a graph, that will give me my beam spread. What will be on the vertical axis? It will be my distance or thickness. Here, it will be my beam diameter. If I get this value and I plot it on a graph sheet or electronically plot it, you can use any of these UT softwares to plot it, or you can use even Excel to plot it and you get your beam spread, or physically get a graph sheet and you plot it. You will get the physical beam spread. You can measure the angles. You can, after getting the graph, you can measure the angle. This is very easy to get. With this distance, let's say this is, I take this as a right angle triangle. If I get this distance opposite over adjacent or whatever you do, because this, if this is the angle, this is opposite, and we know this distance, which is adjacent, we can work our way back and physically get this value that we calculated earlier with the formula. So how do we do that for beam spread? You can use this side drill holes, or in other cases we have a bottom drill. So I have 4 side drill holes here. 1, 2, 3, 4. I can use these 4 holes to do my beam spread. How do you do it? So if I have a side drill hole and I put my probe, when the probe is at the center, we normally say the intensity of the beam at the center is at the highest. So if I have, say this is my probe, physically looking at, will demonstrate it shortly. Say this is my hole and this is my probe. At the center, I will be getting the maximum echo height. And we're told that by the time you move your probe to either direction, left or right, and this maximum echo drops down to 50%. So if this is say, maybe it's at 80% FSH, and it drops down to 40% FSH, which is 50%, that is the end of the spread. So which means I put the probe, I move it this way until my echo drops down to 50%. I also move it to the other direction. That will give me my beam diameter. It is an approximated value. So if we want to practicalize it, so this is the echo in question. This is the echo in question. If you look at it, by the time I go, it's dropping, it's coming up. So if I come to my dB value and I reduce my dB, let's say now it's at 80%. Is it maximized? So I'll keep moving back and forth. It's going down, it's coming up, it's maximized. So it's maximized at this point. If you really look at it, you will see that the probe center is aligning with the center of this hole. So what you will do, you sweep. So here is at 100%. I can still reduce until I get to about 80%. You take your pencil or your marker, you mark the center of this. You see it's aligning, you mark it. You move this forward a little until it gets to 40%. So this is 40%. I will mark with this center that I marked, I will align it to this point. So when I move it to this point, I will align and I will mark where it ended here. I will come back until I get to this full 80% again. Take it back to this other way and mark it. So on your block, you are going to get a distance. You can use a pencil. So I will get a distance. How did I get this distance from the center? I move it until I get to 50%. I mark. So the first step is you put it here at the center, you put it here and get the maximum at 80%. You move it this way until you get to 40. You mark with the center. You move it this way, you get to 40, you mark the center. That gives you the beam diameter. So which means we are going to have a beam diameter, or we can say depth, beam diameter. The depth is easy enough. You just get your rule and measure this distance from the top to the center of the hole. So let's say this is 15. Then you measure this distance that you got by moving your probe left and right and record it. Let's say 25. So you are getting a depth and a beam diameter. You go the same thing, you do it for the 4 holes. Take note, start from the lowest depth and end with the highest depth. What you will discover is that as the depth is increasing, the beam diameter that you are getting will be increasing. So you record all the value at 15, at 25, at 35, or at 7.5, whatever the distance at 50. You put the diameters. Then you go to your graph and you plot it. By the time you plot your graph, you are going to get a graph that is like this. Somebody will ask, how do I plot it? You remember we said on the vertical axis you have our distance. So you can get 5, 10, 15, 20, up like that. Here, this one, you mark also get distance. But the difference here is this. You are going to get a 0 point that coincides with your center here. And draw a center line here. So for each of the beam diameter, if it is 25, it means I'm going to take 12.5 this way, take 12.5 this way. If it becomes say 50, it means I'm going to take 25 this way and take 25. So for a distance of say 15 mm, so let's say this is 15 mm. So I'm getting my 15 mm here. So 15 mm is going to come at this point. 15 mm gave me 25. I'm going to measure 12.5 this way and measure 12.5 this way. Now, if you really look at this, our distance is increasing, so you can reverse it. So instead of having 5, 10, 15, you can do 15, 20, or you can invert it. If you invert it, it becomes like this. But going this way, we can have 15, 25, 30, and as you do that, you will see that your beam diameter will increase. By the time you plot it, you will get your beam spread. This beam spread should coincide with the one you calculated. By the time you calculate the angle from this beam spread, that verifies that your beam spread is indeed okay. It's something you can demonstrate practically on your own. Get a probe, get an IOW block, and you can plot the beam spread. This is for the 0 degree probe. I hope we've learned one or two things. Thank you.